Hi, welcome to a new video on chemistry. Imagine for a moment that two teams of people are exactly of same strength are involved in a game of tug of war, just like this over here. So if they are exactly of same strength, what's going to happen? The rope will be static. It will not move left, it will not move right. But that doesn't mean, as the rope is static, that doesn't mean the teams or the people are not pulling it. There is always a tension in the rope from left side and from the right hand side. This kind of situation is called a state of equilibrium. If you Google the meaning of equilibrium, you would find a state in which opposing forces or influences are balanced in two states called equilibrium. So what is that? If you Google it, you're gonna find this meaning. A state in which opposing forces or influences are balanced is called equilibrium. Now for a chemical reaction, what's going to happen? For a chemical reaction, this equilibrium or this definition would be a little bit different or on the basis of a reaction. So for a chemical reaction, the equilibrium is, so for a chemical reaction, equilibrium is the state in which the rate of forward and backward reactions are equal. So here the thing is, or the phenomenon is almost like the tug of war, but here what is happening? Two reactions are working at the same time, or you can say a same reaction is trying to move forward and as well as trying to move backward. Just like the tug of war, two teams are trying to pull the rope towards themselves. So here the rate of the forward reaction and rate of the backward reaction are exactly same. That is called the equilibrium. Just like in the tug of war, the rope was in a static condition. Okay. As this kind of process or the chemical reaction is always moving, or this kind of process is always in motion, we can call it another name which is very important for the chemical reactions or chemical equilibrium is called dynamic equilibrium. So we can call this thing is also dynamic equilibrium. Suppose if we consider a chemical reaction, okay, if we consider a chemical reaction like this, where A is a reactant is reacting with B, and they are forming C plus D, and the rate of the forward reaction is R1, rate of the backward reaction is R2, okay. Then for this reaction, the equilibrium means at equilibrium R1 should be equal to R2. That is it. Now in the tug of war game, to indicate the midpoint of the rope, a small piece of cloth used to tie with the rope, which indicates which team is pulling more. But in the chemical reaction, there are nothing like this. But in the chemical reaction, the role of that small cloth at the middle of the rope has been played by the equilibrium constant, which is indicated by K. K. Which, unlike the tug of war, expresses the relationship between the products and the reactants at equilibrium with respect to a specific unit. Okay. Now if we consider a chemical reaction like this, just like the last one, this one, that is only difference is here we are putting the stoichiometric coefficients. These small a, b, c, d are stoichiometric coefficients. Small a, b, c and d are stoichiometric coefficients. And what this stoichiometric coefficient exactly is, it's actually representing the number of moles or number of molecules of the reactants and products. That is, how many molecules are reacting with how many molecules to form how many molecules of different products. Okay. Or on the other hand, you can say it is representing the number of moles of reactants and products respectively. Okay. Now the ratio of the concentrations of the products upon the reactants at any moment during the reaction could be written as this. Like this, and this Q or the ratio of the concentrations of the products versus reactants are exactly called reaction quotient. This Q is exactly called reaction quotient. But if we are considering the same thing at the time of equilibrium, this Q, the reaction quotient, will become K, the equilibrium constant. Actually, equilibrium should be expressed with respect to activity A. Just like this, I am going to write it down over here. actually equilibrium constant should be expressed with respect to activity or A, like this. K equal to activity of A to the power A into activity of B to the power B divided by activity of C to the power C to activity of D to the power D. Okay, the activity rather than the concentration. But the relation between activity and concentration is actually equal to this. A, activity equal to gamma into concentration C. What is this gamma? Gamma stands for the activity coefficients, right? On dilution or for a very dilute solution, what is happening? This gamma is approximately equal to 1. It's becoming 1. So in that case, A would approximately be equal to C, right? In practice, it is easy to deal with the concentration than activity because we need to carry forward this gamma, and if you are trying to carry forward this gamma, ultimately you are just trying to make the calculations and everything more complicated. So that is not our desire. Now if we consider K or equilibrium constant with respect to concentration, it should be termed as Kc, which is equilibrium constant with respect to concentration. But if we are involving the reaction, but if the reaction involves gaseous component where the pressure is the determining factor, then it's termed as Kp or equilibrium constant with respect to pressure. So in that case, what's going to happen? This Kp, because Kc we have already considered, it is the ratio between the concentrations at equilibrium constant. But Kp, if the components of the reaction are gaseous, then what's going to happen? Then it would be looking like which is called reaction quotient. But if we are considering the same thing at the time of equilibrium, the reaction quotient will become equilibrium constant K over here. Actually, equilibrium constant should be expressed with respect to activity. Okay, so we are gonna see how it's looking like if we are expressing the equilibrium constant with respect to activity. So in that case, equilibrium constant K would be equal to activity of the product, that is activity of C to the power C into activity of D to the power D divided by activity of A to the power A and activity of B to the power B, right? This is the expression, and the relationship between activity and concentration could be written as this: A equal to gamma into C, where gamma is called activity coefficient. Now for a very dilute solution, this activity coefficient will approximately be equal to 1. So in that case, we can write A is equal to C. In practice, it's easy to deal with concentration than activity. Why? Because if you are dealing with concentration, you don't have to carry forward this gamma thing or the activity coefficient, and that will help us to simplify the calculation. So for the sake of simplification, we are going to use, or we are going to think about a very dilute solution where activity is exactly equal to C. Okay. Now if I consider K with respect to concentration, then that is the equilibrium constant is termed as the ratio of the concentrations of products by reactants. Okay. So in that case, it would be termed as Kc. So in this case, if we are trying to write it down, it would be looking like this. That is concentration of C to the power C, concentration of D to the power D, divided by concentration of A to the power A, concentration of B to the power B at equilibrium. At equilibrium. Now on the other hand, if the reaction involving some gaseous component, in that case what's going to happen? For that case, concentration measurement would be a little bit difficult, it would be challenging. So in that case, for a gas, the easiest way to measure is the pressure, the pressures of the gas or the partial pressures of the gas. So in that case, if you are trying to express the equilibrium constant with respect to the pressure of the reactants and products, in that case we are going to express it in terms of Kp, equilibrium constant with respect to pressure. So there it would be partial pressure of C to the power C into partial pressure of D to the power D, divided by partial pressure of A to the power A, partial pressure of B to the power B, like this. Now the relationship between this Kp and Kc could be written as this: Kp equal to Kc into RT to the power delta n. Now to get this relationship, there is a very common thing we need to consider over here, that we need to consider all the gaseous components are ideal in nature. Okay, so what we are doing over here, we are considering ideal gas mixture. Otherwise this relationship not going to work over here. Okay, and this relationship Kp, Kc are the equilibrium constant with respect to pressure and concentration respectively. R is the universal gas constant, T is the temperature, delta N is the difference in number of moles of product and reactant, or you can say it is the number of moles of product minus number of moles of reactants. Another beautiful thing is the involvement of water. If in a reaction which is occurring in aqueous medium, then most of the portion of the reaction mixture is water, more like our human body. At that time, we could consider that the concentration of water is not changing with the concentration of the other constituents. At that time, we are going to consider the water or the concentration of water as 1. And we are going to, in the future videos, we are going to experience that in time and time again. So in here, I would like to wrap up today's video over here with this thing, that if water has been considered over there, in future we are going to introduce another term, which is the order of the reaction. At that time, as the water is not involved in there in the expression of equilibrium constant, we are going to call it the pseudo order. What is the pseudo order? That we are going to discuss in upcoming videos. So thank you very much for listening, and we're gonna see you again in the next video. Until then, bye bye.